Alrighty, here we go. So, that when we started derivatives, we had a whole bunch of properties about derivatives, and in fact, derivatives represented three different things. Any guesses? Slope of what line? Tangent. Slope of the tangent line. It's a good thing we're reviewing. Instantaneous velocity and rate of change. Okay? So, yeah, it's always easy to say, oh yeah, after I told you oh yeah, that's, you know. Today we're going to learn about one of the properties of an antiderivative, i.e. integral. And we're going to start that idea by talking about something called the Reimann sum. Okay? This is fairly easy. It should be fairly easy. Don't make it more complicated than it has to be. Okay? So let's go through our objectives, and then I'll fire up that program that I've used before. So we're going to talk about area. We're going to talk about approximating the area, and we're going to talk about how the area relates to limits. And then by now you should be able to draw that squiggly symbol. Okay. So before we do that, the blue is the first property of an integral that we're going to make full use of, and that is the integral represents the area under a curve. In other words, it's the area from the graph down to the x-axis. And there's a whole bunch of different ways to find that. There's a whole bunch of different questions, like what happens if it goes below the x-axis? What if the function is below the x? You know, we'll cover all that later. I just want to talk about this basic idea. Okay? The problem with us right now is that we know how to do an integral. We know how to do a lot of different integrals. You've done it already. But every one of those integrals gave us another function. Okay, so for instance, the antiderivative of sine is negative cosine plus c, right? So for us right now, the antiderivative represents another function. But you're not stupid. You realize that the area of that blue region in that picture is a numerical value. So how do we get from an integral to a numerical value? And that's what we're going to talk about for the next couple blocks. Okay? But we're going to start very simple here. We're going to use some ideas that Reimann talked about. This is a mathematician named Reimann. I don't know his first name. Let's put this aside for a second. Let's close this. Stop it. Okay, and let's go to this guy. Where is this? Go away. You move. Go here. Okay, so Reimann did this. He said, I have this red curve, and what the function is not important right now. He said, I want to find the area under the curve. And so he starts with something ridiculous. He breaks the area under the curve into two big rectangles. Why rectangles? Well, because rectangles are easy to find the area of. Okay? I'll ask you an obvious question. Is that a good representation? Are those blue rectangles a good representation of the area under the curve? Okay, good. Right. Why? Well, you got a bunch of blue above, you got a bunch of white below. So what can we do to make it more accurate? If I increase the number of rectangles, you can see that we get closer and closer to the actual area. So now, if you're sitting in the back of the room and you look at the front of the board, all of a sudden that looks like a pretty good representation. It's hard to see the little corner points on the rectangles. It's hard to see any white below the curve or any blue above the curve. And that's all we're going to do today. We're just going to talk about rectangles. Any questions so far? Okay. Now, let's go back to the question about why rectangles. Well, would triangles make any sense? No. Are there any other geometric shapes that... Okay. Trapezoids would make an excellent example. And in fact, we're going to get to trapezoids later after we've mastered rectangles. Okay? Circles are ridiculous. Triangles are ridiculous. Pentagons, even more absurd. Okay, we're going to stick with only rectangles and only trapezoids. Okay, so you understand the concept here. Now, if I go back to something a little easier, these blue rectangles are called right-hand rectangles because you'll notice the right-hand side of the rectangle is what's touching the function. Okay, so if I look at this blue one over on the side here, the right-hand side of the rectangle is what touches the graph. If I go to this little blue one over here on the far left, the right-hand side touches the function. We can flip that, and we can do left-hand rectangles. And we get something like that. Now the left-hand side of the rectangle is what's actually touching the function. Okay, so far? Now we'll get into the nitty-gritty of how you figure those out in a second, but I want you to understand the basic concept. So in that picture right there, I have 11 rectangles. And there's a bunch of wasted space. By wasted space, I mean there's white area below the curve, there's purple area above the curve. How do I get the most accurate answer possible? Yeah.
By splitting the rectangles up into smaller rectangles?
Excellent. So the answer to the question is, you can answer the question two different ways. What I heard you just say is, let's make smaller rectangles. Excellent. That would be the same thing as increase the number of rectangles. Make sense? Okay, and either one is a correct answer. As I increase the number of rectangles, the wasted space gets smaller and smaller and smaller. If I wanted an exact answer, since this is a calculus class, what would you then do? How many rectangles would you like, Liam?
Infinitely many.
Infinitely many. And you smell that? It smells like a limit. We'll get to that later. We would like we can do this a couple different ways. Getting back to how Leona answered, we could take the limit as the number of rectangles goes to infinity, or we can take the width of the rectangle going to 0. Good. Okay? So, general concept, are we good to go? Okay, excellent. Now, let's just talk about how we do that. Shut up. Okay, come back here. There we go. Okay, so there's our curve, right-hand rectangles. I don't remember. Okay, good. If I have 5 rectangles, and I go from 0 to 10, how wide is each rectangle? 2. How'd you get that?
10 minus 8.
Say it loud, say it proud.
10 minus 8.
No.
Wait.
The answer is 2. Well, why is it 2? Yeah.
Well, you can use 10 divided by 5 because there's 5 boxes.
Okay. Suppose I started at 2 and I ended at 20 and there were 5 rectangles. How wide would each one be? Start at 2, end at 20, I have 5 rectangles.
You do 20 minus 2 over 5, so 18 over 5.
Beautiful. Okay. That value, the width of these rectangles, we're going to call delta x, and you get delta x by doing that. Okay, so let's get some notation under control. Delta x is the width of the rectangle. A is our starting point. B is our ending point. N is the number of rectangles.
Maybe it's ending.
Hold on. Why isn't my pen working? Okay, come on, Reedy. 5 days off and everything falls apart. A is starting point. B, ending point. N, number of rectangles. Most of the time, we're going to start at 0 and end at some number.
Wait, what's delta x?
Delta x, width of the rectangle.
Oh.
doesn't always have to be a pretty number. Start at 0, end at 10, use 15 rectangles, all of a sudden we get fractional values. That's okay. Delta x can be just about anything. Okay, we good with that concept? So now we can figure out how wide the rectangle is. Let's take one in particular. For no obvious reason, I like this rectangle right here. And if I said to you, I would like to know the area of that rectangle, how would you find it? Beautiful. You must have had a good geometry teacher. Base times height. What's the base of that rectangle? 2. Also known as? In general, sorry. Delta x, right? How tall is that rectangle? Joe?
Roughly 8.
Roughly 8. So where'd you get that value, Liam?
I looked to the side where there's the numbers, and it's about 8.
Notice it hits the function at that point. That distance is the height of that rectangle. How do I find the height of that rectangle? In this case, Liam looked at the graph and approximated it somewhere about 8. For us, it's going to be the value of the function, because notice that point is on the function. So this is at 6, so therefore the height of that rectangle would be f of 6. So we are going to use the function to approximate this area. And as I've mentioned already, this picture is a horrible approximation. There's all kinds of wasted space down below there. Okay, but we got to start somewhere. And we're going to start simple in the fact that all of these rectangles, delta x is going to be the same for all of them. Notice all 5 of those rectangles had the width of 2, which makes our lives a lot easier. Later on, we're going to talk about what happens when the rectangles have different widths. Okay, but that's later. Okay, any problems here? So just to make sure you're on the same page, how would you find the area of that rectangle? Lauren? F of 2 times 2. Perfect. Or better yet, f of 2 times our delta x if we talk about general equations. Good. So the KISS method comes into play here. Keep it simple, stupid. To find the area under that curve, just find the area of a bunch of rectangles, which you can all do. Questions? We're good? Excellent. Abby, hopefully this writing shows up on the... Abby was absent the other day when the last lesson I taught, and it turned out I was using the writing that pops up here, and apparently it doesn't show up on the video. So hopefully this one works. Otherwise, I'm quitting. Okay, so left-hand rectangles. Now, I changed this a little bit and made it all fancies in my pansies. Each of those rectangles would be found by doing base times height. Well, if they all have a base of 2, I can factor that out. Then it's just f of 0 plus f of 2 plus f of 4 plus f of 6 plus f of 8. Okay? Different colors. What do you notice about this picture?
It's the right hand.
Good. Now, number 1, it's a right-hand rectangle. What else do you notice?
It's like there's space over instead of under.
Correct. You will commonly hear the question, is that Reimann sum an overestimate or an underestimate? Meaning, if I go back to this purple guy, the actual area under the curve would include all that white space below, but this would be an underestimate. If I go to the blue one, I have an overestimate. The concept is the same. How wide is each rectangle? Well, I'm going from 0 to 10. I have 5 rectangles. Each one is still 2 units wide. And then how I find the area is going to be different. So if I look at this first rectangle, how do you figure out the height of that rectangle? F of 0 or F of 2? Say it loud, say it proud. F of 2, good. If I pick the middle rectangle, how do you find the height? F of 4 or F of 6? 6, correct. Okay. Now, for those of you that are confused, it's real simple. Ask yourself, where does the rectangle, which corner of the rectangle is touching the function? Okay, so this middle one is touching on the right-hand side, so you use that value of F of 6. Right-hand rectangles, approximating by. Okay, now what I want you to look at is this function at the bottom compared to that. Notice the purple one starts at F of 0 and ends at F of 8. And because there's 5 rectangles, there's 5 of these. The blue one starts at F of 2 and goes up to F of 10. It has to do with which side of the function touches the actual, which side of the rectangle actually touches the function. The number of these F of things has to match the number of rectangles. Okay? How are we doing? Is this a pretty easy concept so far? We're good? Okay, because I know you can all find the area of rectangles, so let's see if we can put that to work. I've got this function. In this case, I happen to know the function. It's 1/2 x squared plus 2. And I want to look at the interval from 1 to 4 and approximate the area under the curve using left and right endpoints. Let's just do the left one first. Okay? So I'm going to take you through this and show you how I do it. And hopefully that will help you when it becomes your turn to do it. I think the secret of this is drawing a nice picture. Okay, or drawing an accurate picture. Does that mean you need to accurately graph everyone? No, but it will help. Okay, so I know first of all I'm going from 1 to 4. My first one is going to be here at 1, and at 1 I'm going to draw a vertical line up to the graph. And in fact, I'm going to draw a vertical line up to the graph at all the points. So 2, 3, and 4, and I start the problem by just doing this. Now I'm going to start with a left-hand rectangle. So a left-hand rectangle means I go up the left-hand side of the rectangle. My first rectangle starts it's the rectangle from 1 to 2. So therefore I go up the left-hand side and hit 1 and come across. This is my first rectangle. Any questions on that? Move to the second rectangle. Go up till it hits the function and make that thing appear and come across. There's my second rectangle. Up here, there's my third rectangle, and I'm done. So now I've got a pretty accurate picture of what my problem looks like. And you see, that's a horrible approximation, but we don't care. Questions so far? Beautiful. Let's start by doing delta x. Delta x is 4 minus 1 divided by 3. Oh, look, delta x is 1. I chose some pretty numbers. Rectangle number 1. Actually, I lied. Come here. Where's my...
On the right side.
Oh, why is it over there? I'm left-handed, don't they know that? It is. It just depends on what side you click on first. Okay, area of region 1. So I'm going to call this region 1. This is region 2. This is region 3. 1 times f of what? Am I using f of 1 or f of 2? 1. Good. Don't rely on the picture. I gave you the function, so use the function. What's f of 1? Two and a half, also known as 5 halves. Okay, so this is f of 1, which equals 5 halves. Let's stop there for a second. Any questions? Nope. Beautiful. Area of region 2. What's what?
Area 1.
Oh, area.
Area 1. Yeah. Area 2. Delta x didn't change. It's still 1. F of The middle rectangle, I went up the left-hand side, f of 2. What's f of 2? 4. Excuse me.
Oh boy. I gotta quit smoking. Area of region 3.
1 times f of 3. F of 3 is 13 halves. So my Reimann sum total would be 13. Yes? Okay, good. Any problems? Okay, now your turn. Do the same thing, but now do right-hand rectangles. And I don't remember what I showed you in the slideshow. Do you have a pic? Yeah, so if you go to the next slide, I've got a picture of the, I didn't vote, didn't I? There you go. Go 2 slides forward. In fact, I can do that too. And I already drew the picture for you for the right-hand rectangles. What I would like you to do is find the area of those. Okay, so there's the left hand we just solved. Blah, 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 blah. There's the right-hand one. So find the area of those red rectangles, please. By the way, will the answer be bigger or smaller than 13? Bigger, good. The first one was an underestimate. The second one, this one is going to be an overestimate. When you get done with your calculations, check with your group to make sure you all have the same answer. What do you get?
Oh, I got that. Oh! That was a weird number. Yeah. I thought it was a weird
Kush, what do you got? Anybody else? 20.5. Hot diggity. Kush, I'll save you the hassle. I'll just talk you through it if you don't mind. Found the delta x again. We all know it's 1 because we're fairly bright. Nothing changed there. And then I did all that fun stuff. Okay. Now, I combined all the f of statements and then just multiply by delta x. You don't have to do that. Just break it into rectangles, which is what I saw most of you do. Okay, find the height of the first rectangle, find the multiply by delta x. Find the height of the second rectangle, multiply by delta x. Find the height of the third rectangle, multiply by delta x. Add them up. We're done. Any problems? Okay, good. Don't make this more difficult than it has to be. This is it. This is all we're doing for a while. Okay? Yeah. Well, we're not quite done. I got a couple other things. I got some terminology to teach you. Okay? So, we have these things called upper and lower sums. This picture pretty much sums it up. Little s, lowercase s, is called a lower sum, also known as inscribed. So from geometry, you remember the words inscribed and circumscribed. Inscribed, drawn inside. Circumscribed, drawn outside. So when all the rectangles are below the graph, That's called a lower sum or an inscribed Reimann sum. Lowercase s. Uppercase S is the exact opposite. All the rectangles are above the curve. It's an overestimate, and we call that uppercase S. Okay. Now notice, let's look at the picture all the way to the right. If I pick one of those rectangles at random in that picture, let's say for instance, this guy, okay, that's a circumscribed rectangle because it's above the curve. You're with me, right? Is it a left-hand or a right-hand rectangle? Left. Good. Pick a different rectangle. Let's pick, in a lovely shade of blue, we'll pick this guy. Still circumscribed. But now, right-hand rectangle. So one of the things we're going to talk about in the future is, how do I know if a rectangle is inscribed, circumscribed, left, or right, and is there a relationship between those? And the answer is yes, and we need to talk about what that relationship is later. It will have to do with the shape of the function. Is the function increasing? Is it decreasing? Is it concave up? Is it concave down? That will affect the rectangles. For now, all we care about is, let's just find the area of those bad boys. Okay? Questions? More of the same stuff. Now, this one, okay, so before I talk about what I was going to talk about, let me ask you a question. The left picture, well, both of those pictures, what can you tell me about the actual function, the right, or the black line? Is it increasing or decreasing? Increasing. Is it concave up or concave down? Concave up. Okay, so notice, if it's increasing and concave up, those left-hand rectangles in the first picture are also inscribed. In the right picture, we've got an increasing and a concave up function. The right-hand rectangles are circumscribed. Okay, so it kind of gives us a hint at what we're going to talk about later, because eventually we want to be able to go back to this picture and notice this picture is both, it's all increasing, but it's also concave up and concave down, and things switch around. We'll worry about that later. Right now, what we want to worry about is finding area. Okay, now, we're not going to do this example because we just did this example, but the only thing I changed in this case is the number of rectangles and the location of those rectangles. So notice I'm doing 4 rectangles now, and I'm going from 0 to 4. It will affect the outcome, but the process is exactly the same. Figure out your delta x, calculate the area of the rectangles, add them all up. Okay, and the same is true with that, and then we get to this bad boy. Okay. Does anybody know what that big E-looking thing is called? Oh, I'm an idiot. I put it in the title of the slide. That's called the sigma. Do you know what it means? Say again? It's a sum. Right. This is, as it says up here, this is an old school notation. And I usually don't teach this because it's old school. Nobody ever uses this anymore. Except last year, it showed up on the AP test. That was awesome. So I just wanted to go over this quickly. We're not going to do a lot with it, but what does this mean? That's basically the way that Reimann wrote out his idea of Reimann sums. Okay. Why? What does this mean? This means take the width of the rectangle, which is delta x, multiply it by the height of the rectangle, which is f of x, and then watch your sleeve on the screen, and then add up all those rectangles. Okay, so the sigma means add them up. You add up the rectangles from the first rectangle, I equals 1, up to n rectangles. And that's what we've already talked about. It's just a different way to write it. It's not, like it says, it's old school, nobody uses it anymore, except, of course, last year on the AP test. Okay, so I wanted to make sure you've seen that at least once so you understand what it's doing. Just a fancy way of saying find the area of the rectangles, add them all up, we're good to go.
Did you teach them this last year?
Yes, I did.
Oh, okay, so they didn't get all get it wrong.
It was like one multiple choice question when it showed up, and most of them were able to guess correctly. Before I even mentioned this, you knew what a sigma does, right? You've seen it in other classes? Okay, so you probably could have BS'd your way through the problem, which is what most of my students did last year. Whoops. Okay, we're done. Now, before the end of the period, hold on. Let me stop the recording here.